Hello, welcome to my space station. Today let's talk about the P versus NP theory, or more like a question. So this is a very fundamental question in computer science, and it mainly deals with computational complexity. So what this basically is, what computational complexity, the field of computational complexity inside computer science basically is that it deals with how much time the algorithms and the programs would take depending on the input size. Now, there are many different ways of measuring the time. The most widely used way is the big O notation. Basically, you have n, and n increases as the input size increases, the size of n also increases. So the smallest size is n by itself, and the biggest size is n factorial. So, but the bigger the inputs and the bigger the algorithm is, the more time the algorithm takes to give you the output and the solutions. So this is a very basic concept, and what the P versus NP theory is that it deals with two class of problems or algorithms. Now each solution has an algorithm behind it. Now an algorithm is a set of instructions, usually as in source code that are used to carry out an operation. So there are two classes, class P and class NP. Now class P is short for polynomial. Now class P basically is the class in which the questions there are, they can be solved in polynomial time and verified in polynomial time. Now, when we talk about polynomial time, it means time which is like comprehensible, like a few seconds, a few minutes, a few hours. Past days and weeks, it comes into the class of NP. So, now some examples of the problems inside the class of P are addition, multiplication, division, prime factorization. These are the things that are very easy for a computer to solve and can be done very fast. So the other class is NP, which is also short for non-polynomial. Now these class of questions are more complicated to solve. Now every single question has an algorithm behind it. So the harder the problem is, the more longer and the more complicated the algorithm will be. So the NP problems are such as solving a Rubik's Cube or finding all of the prime numbers. These are some very exceptional cases where the algorithm is too huge and it takes a lot of time for our normal computers to process. And so that goes into the class of NP. Now NP problems are very hard to solve, they take a long time to solve, but if a solution is given, they can be verified in polynomial time. Let's say take a Rubik's Cube. Now for a computer, solving it might be hard, but verifying that it has been solved correctly, like all the colors are the same, will be easy, right? The computer can easily just check all the colors and say, okay, you've solved it right. Games like Sudoku, they are hard to solve, but the computer can just verify them by adding up all the squares and whatever the processes behind that are. So the question that this problem asks is that, are all P problems essentially NP problems? If given the right amount of time, will every single NP problem be in the class of a P problem? Now there are two sides of the argument. One side says that yes, they can be. Given the right amount of time, if a computer solves the NP problem and verifies it, it can be characterized as a P problem. And there's a separate category for that called NP completeness, which means that the NP problem has been confirmed to be a P problem and it's put in that class. And the other side of the argument is that no, a computer will take, now the other side says that P is not equal to NP and that a computer will take too long to solve that question. Even though verifying it might be quick, it would take too long to find the answer. So both of the sides have different proofs. One of the biggest proofs used that P is equal to NP is that like computer algorithms have been developed to solve Rubik's cubes, and nowadays they are pretty fast. So that's one of the like proofs that P does not equal to NP. That a computer now can solve Rubik's cubes, and as AI is advancing, they can also solve Rubik's cubes. And the second part, the thing is that most of the people believe that P does not equal to NP. Reason being is that most of the problems, like take Sudoku and all, a computer will take a long time, even though it will solve it in the end, it will take too long to be acceptable in today's world. So that's why the majority of people believe that P does not equal to NP. Now, one question that constantly comes up in people's mind, if we have found a solution, take the Rubik's Cube, that equals P is equal to NP, why isn't the entire problem solved? The reason being that just because one problem is solved doesn't mean that this logic applies to every single other problem that exists. Now, this used to be the case when people believed that there is a circle of P and NP problems. If one is solved, that would necessitate all others being solved. That is not necessarily the case. Some people do believe that that's the case, but it's not always the case. That's why we don't believe that the problem has been solved yet, because not all major problems have been given enough proof, enough reasoning that P is equal to NP or P does not is equal to NP. So understanding this problem might be easy, but solving it is pretty hard. That's why in a long time, this problem hasn't been solved, and that's why many people are now assuming that it's gonna be AI, maybe Chat GPT, GPT-10 or something that ends up solving this amazing problem. But solving this problem, as hard it may be, has its consequences and advantages. So let's assume that for the sake of this video, that someone finds out the answer that P is equal to NP. They provided sufficient enough proof for that, and let's say we have completed the problem. Now what? Now there's two sides of the argument again, two sides of the coin again. There are some advantages and there are some disadvantages. One of the main advantages is that computers will be even faster than they are before, right? Because then we will develop algorithms to solve those NP problems even quicker. That's how we eventually proved that P is equal to NP. So that means that algorithms would get faster, AI would get smarter. A lot of these things will happen. The future will look bright. That's all fun and games until you get to the second side of the argument of the coin, which says that P is equal to NP would be a disaster. 128-bit security would break down, meaning that since the computer is now so fast, you can crack all of the encryption, right? Hackers will be able to get into hackers will be able to get into the big databases, and security won't exist. There's so many things like that, and the world which we thought was protected by these firewalls and all, they will also break. So P is equal to NP might be a fun scenario to imagine, but it's also a pretty dangerous one. Humanity will be in a great danger if P is proven to be equal to NP. And if P proven to not equal to NP, that would have slightly less disastrous consequences, but that would mean that there are some problems which computer can't solve. And like I discussed in the Moore's law video of mine, we would be proving to ourselves that we have hit the limits of computer advancement. So I hope you enjoyed the video. I hope you learned a bit about the P versus NP problem, and I hope one day we are able to solve this problem, whether it goes for the good or the bad. Thank you for watching. Bye bye.